Welcome to Def and episode number 69. I think this is where Ray, I expect some comment from you.
Well,
episode number 69.
I think the kids are going to love it. That's all I mean.
Yes. And this time we're going all the way back to the beginning. So we got our first guest in 2016. When was it again? June 2016. And now after seems like 4 years and a millennium because of 2020. Now we are back to, we invited back our first ever guest on the show. Welcome back to Def and Mike Fikes. And how do you feel about being part of this amazing episode number?
Oh, hey Vijay, hey Ray, yeah, my son is gonna love it. I can predict that. I was hoping that this would occur. I'm like, yeah, pick me for that episode. Yeah, succeeded.
Full circle. It's a full circle episode. Nice. So I think plenty of things changed since 2016 already. Yeah.
So I was trying to remember what I was talking about on that last episode, and the only thing I can think about is I remember in 2015 was when self-hosted Clojurescript kind of became a thing. And I think after that, several things were created surrounding that, and that's probably what we were talking about. Yeah. Various self-hosted REPLs and things like that around that time frame.
Yeah, it might have been the replete thing for iOS or things like Plank and Lumo and stuff like that. Maybe Lumo wasn't even around yet.
Maybe.
And I think what fundamentally allowed that all to happen, I think part of it at least, was the fact that reader conditionals were added to Clojure. So that's about how long ago it was. That was right around the half a decade ago.
So what has been happening since then? So most recently, I think maybe we should go. It's much difficult to think about going through all the stuff from there. Maybe we should start with the recent ones that you're working on.
That's all I have a memory of anyway. Like my memory doesn't work longer. I
mean, 2020 has been long.
Yeah, man. So I joined a company with Ray, full disclosure, right? Everyone knows that, named Vouch. And that's what led to the thing that we're going to talk about, which is we were getting into like microcontrollers for some reason. We were digging into like making our software, like getting our software's tentacles into every place we could. And it turned out that building hardware was kind of an interesting thing for us at Vouch. And Vouch is pretty much a Clojure shop, right? Pretty much. I don't know if you'd agree, Ray.
Oh, yeah, definitely.
But we were faced with, oh man, the whole microcontroller thing, that's pretty much C or whatever, or Rust, maybe if you're fancy, right?
Yeah.
So even before then, we were talking about like, what if we could somehow get some sort of Clojure dialect to run on these microcontrollers, so that we don't have to like face the pain of writing stuff in C, really. I mean, I like the language, but man,
Yeah. But so Clojure I think Clojure started like the back end and then front end and then front end, back end, and then all the way to all the way, I think just say like totals all the way down. So
and for me, interestingly, like the whole Clojurescript thing was really, I've never ever been a web developer, really, and yet I have a huge thing to do with Clojurescript, but I've never done that web thing. I don't develop web pages. I did once in anger, and I walked away from that. So for me, Clojurescript has always been like, reach, that whole reach argument that Rich has of where that language can go. And it's, and for me, initially it was, I was producing iOS apps at the time. This was before React Native. And that was the first thing. That was why I actually got into Clojurescript. Was basically, it was a suitable language that you could use to code and write, execute something inside of a mobile app, inside of an iOS app. And then, so that was not the web. That was, a mobile app, a native app, really. And then things like self-hosted has its own reach in different places. And, but so this whole microcontroller thing is yet another example, I guess, of that reach thing.
Yeah. So maybe, I think obviously I have not much memory of microcontrollers and stuff. I mean, even though I'm an electronics
this would be
engineer.
good. So like ask all the questions you can, because I may easily assume knowledge, right? Or assume that and especially for the audience, because I was the same way just a year or two ago, and I'm like, what? Like, it's microcontrollers are often referred to as MCUs, right? Like those are little details that the audience may not even know.
I think the only MCU that I know is the Marvel Cinematic Universe or something.
Yeah, exactly.
Well, maybe Mike, the thing about it is, like, I think a lot of people think of like these like embedded systems and everything to do with the maker community, and so you've got like this, there's obviously like things like the Raspberry Pi, and what's the other one? The one with the breadboard. What's it called?
Arduino.
Yeah, the Arduino.
Yes.
So maybe as we start there, and because I think the problem with the Raspberry, the nice thing about the Raspberry Pi is it's quite competent actually. It's, for a very small, cheap computer, it's got a lot of capabilities. Yeah. But then obviously you get further and further down. Maybe it's worth just going down the kind of like
So set up the stage,
And that's actually where we were at Vouch. Was we were when we were like we were demonstrating applying our product to unlocking cars at the time, and we had to come up with a way to do that, and we were actually using a Raspberry Pi to do that, and that was great because a Raspberry Pi is effectively a computer. It is, right? It's running Linux, and we were doing that using Node, and we could have been running Java on the thing if we wanted to. It's completely capable of doing all that.
But isn't Raspberry Pi with a it's either Intel, or is it what kind of chip it is using then? CPU?
Oh,
is it
is it an ARM maybe?
Is it ARM? Yeah,
ARM,
probably. Yeah. Okay.
Yeah, and that didn't even really matter when we're doing stuff like a Node and Clojurescript. You don't even see which CPU it is. Yeah.
Yeah, you've got an operating system like Linux, so it's
exactly. So you're like like multiple levels above the stack anyway. Yeah. That's true. Yeah.
And I'm trying to remember what. So we were basically building our stuff on Raspberry Pi, and we were trying to harden it at the time because we were going to start using it to give demos and whatnot. And it's just like you could argue a Raspberry Pi is a little bit fragile. At least the ones I had, it's not in you can buy enclosures, industrial strength enclosures to put a Raspberry Pi within. And they're also,
wait, when you say hardened, you mean physically? Because I was thinking hardened as like security wise.
Oh, no. I just mean physically, like the thing is just fragile where like, for example, you have to be careful not to cut its power because you might corrupt its file system. And I did that. I like lost my file system at one point. So we were like, at the time in Vouch, we were like, is there something that's more robust? And we actually started to work with Bill Hurd at that point in time to help us make some real hardware.
Maybe people don't know who Bill Hurd is, Mike.
Yeah, thank you. Yeah, I just assumed everyone knows who that guy is. Yeah. Okay, so you first of all, do you even know what Commodore is as a company, or what Commodore computers were? Like the whole audience may not even know that, right?
That's true.
So so
especially when we start episode 69 and then we're targeting younger audience. So.
Yeah,
this is the age group that we're targeting.
So, and this thing that we're going to talk about with the microcontroller, it kind of like harkens back to that day where when we were all kids, you would buy a basic computer and you flip it on and it had like BASIC in its ROM, and it like within milliseconds the REPL was up. Effectively, it was a basic REPL. And as a kid, you could start typing and learning. Instant gratification back then, no internet back then. You just flip on your basic computer and start coding. So Bill Hurd worked at Commodore and he designed several computers, but I think the most notable one was the Commodore 128, the one that followed the Commodore 64. The Commodore 64 is the popular one. So Bill basically has been doing electronics his entire life, and he helped us basically in taking what we had at the time and converting it into like a more like, I don't know, a more real, or going down one layer, and making it out of a microcontroller. And because of what we needed to do in Vouch, we needed to basically deal with CAN bus messages in automobiles. Bill basically went and found a microcontroller that could do CAN, and that was the ESP32.
And CAN is like the car network, isn't it? The car area network. So the network of components within a vehicle.
Yeah, basically. So what we were doing is like if you think about those, if you're going to get your car worked on, there's I'll say it wrong, OBD or OBD, ODB, the little jack that they stick the thing in underneath the steering wheel, and they measure like your engine stats and stuff like that. You can get to the CAN bus on a vehicle that way. And on older vehicles, you can actually send some messages across that network and unlock your car. Now, since then, cars have been, the security around cars has been increased, but I have like an old 2011 Prius that you can unlock it that way. So we were doing stuff with CAN, and that was why Bill picked the ESP32. He actually didn't even know about the ESP32 himself. He just went looking around and talked to some of his associates, and they said, "Hey, check out this microcontroller." And it turned out to be a really suitable one. And the interesting thing about that one was it actually it's a pretty capable chip in terms of RAM and processor speed. So it's almost as if when you think about like the Raspberry Pi and then the Arduino, and then you go all the way down to things like you'd normally think of as like the ST or Nordic chips, like the low end things. The ESP32 kind of floats in the middle there somewhere. It's got like a megabyte of RAM, if you get the higher ones, and like same amounts in flash, it's like, it's a pretty beefy MCU. And we had, prior to that, we were always just looking into this thing called Esperino, which is a JavaScript engine for microcontrollers. So we had always thought like, maybe we might get into this world, and we'd had our eyes on this thing called Esperino. And it turns out that once we had picked the ESP32 for the thing we were doing, I thought back to this Esperino thing, and I went and looked and found out, it actually supports the ESP32. And that was kind of like where the kind of like light went off in my head. I'm like, this thing has enough RAM to actually pull it off, where you could run Clojurescript in the thing. Whereas, we had actually been looking at Esperino previously. And we were thinking, man, maybe there's like all types of shortcuts we could do to try to get Clojurescript to seem like it's running on it. So I guess we could talk a little bit about what Esperino really is. And
but so before that, so ESP is the microcontroller, right? The
ESP32 is a microcontroller, but it's also kind of like a
but 32 as in 32-bit, or is it?
It is a 32-bit thing, yeah. And the previous one is ESP 852 something or other. So the name might have something to do with the fact that it's 32 bits.
But what is the I probably asked like plenty of dumb questions, I guess.
Yeah, no, go ahead.
Because I think my electronics knowledge is from, 20 years ago when I actually with my engineering. So
I'm assuming the audience is mostly into Clojure and Clojurescript and may not necessarily even know about these things at all. Yeah. So we can talk
So maybe. So what is the difference then? Because, I know I studied it a long time ago, but there is a difference between microprocessors and microcontrollers, right? So is it like an instruction set or?
So this is where I'm speculating a little bit too. And I think when I think of like the stuff that's inside of all our computers, that's a microprocessor. Maybe it's just the way the terms are used, commonly used. But when people say microcontroller, they typically mean like one of these little embedded devices that's, but to be honest, like what is the real definition and the distinction? I don't know.
I think they're all pretty much the same. They're doing pretty much the same stuff, right? I mean, they have instruction set and then they execute it and they interface with the hardware that you have.
And these microcontrollers typically don't really have like an operating system, or if they do, it's like an RTOS, like a low level thing that like might let you do something with threads or something like that. But it's really like there's typically no file system. There's the typical model for these things for the audience who may not know is you typically write a little C program that can do something, right? It will calculate something or interact with the world through some facilities that the chip may have. And you just compile that program, and that's the thing that runs on the microcontroller. Like a
single program.
They're very, very specialist. So that's the idea. Is they're not general purpose. They're very specialist. They're meant for particular industrial applications for
Yeah.
one or two particular things. Usually to read sensor data or to push to either to read data or to push data to again other small controllers. Yeah.
So ESP32 is the microcontroller that you're using, and now this one can run compiled JavaScript.
Well,
what is the idea between Esperino and this one?
Okay, yeah. So if you say, okay, the main thing you run on a microcontroller is some C program that you wrote, right?
Yeah.
Be it whatever. So you may say, well, what if that C program could interpret JavaScript, perhaps? Like you could, you could feed it strings and it could like say, oh, I'm going to execute these things. So there's several of these kind of things in this class that run, like there are several, target things that will run higher level languages on these things. And one very popular one is like Circuit Python. And there might be another variant to that. So Esperino is basically one of these things that will run JavaScript. And it, there's a handful of these, maybe half a dozen of them. And I don't remember the names of all of them, but Esperino, the way it works is it's not really interpreting the JavaScript. It actually like parses it down and puts it into some internal memory representation inside of it. We could talk about the how, but really that's what it does is basically you can say, oh, if you get Esperino, you can put it on not only just the ESP32, but other even smaller microcontrollers.
Oh, wow.
And once you do that, you can basically connect to typically when you're working with microcontrollers anyway, you connect to them using some sort of serial cable, like a USB cable you hook to it. And then you can basically type commands to it through a terminal. And Esperino basically makes it so that you're basically at a JavaScript REPL or prompt. And you can you could type in 1+1 and hit enter and you'll get back 2.
Okay.
And so it's actually surprisingly performant. It actually, it's not blazingly fast, but it will execute JavaScript. And it, I guess I'm going to slip into talking about the how again, but it's kind of
go ahead.
It's kind of interesting technically. It actually, it mainly is really, really, really concerned about RAM, preserving RAM. Because that's the, you might think, oh, you don't have much CPU power, but really the main constraint is RAM when you're talking about those kind of things. You may only have like kilobytes of RAM, or several hundred kilobytes of RAM to run things in. So what it's doing is Esperino is pretty clever, and it takes your JavaScript and compiles it down to very efficient in-memory representations. And as a matter of fact, there's a cool thing on the Esperino website where they talk about like, what is the smallest way that you can represent an algorithm? And they take like the bubble sort or some algorithm that you can imagine is like 15 lines long. I can't remember which one it is. And they represent it in different languages. And they look at like, well, what if you were to just write that thing in C and then get the machine code associated with that, right? And they showed that minified JavaScript is smaller than the machine code generated by a C compiler. It's like, it is the most compact thing that we as humans can produce right now. And maybe that makes sense because we've all evolved to make JavaScript ship to browsers, right? And we can compress it down to almost nothing. So it is the most efficient way as humans, as we know right now, to express algorithms is minified JavaScript. I know it's kind of funny. And that's effectively what the Esperino kind of leverages is the ability to represent its code in the tiniest way possible to fit it on those small things. And then it just arranges to execute it somehow.
Okay. So when you write a program and then you compile it, quote unquote, compile it down to JavaScript, then that's what that is being stored in RAM because you need to read it from RAM to execute this one, right?
So like if you imagine like if Esperino is running along and it hits a new function that it needs to, like your one function calls another function, it's not like looking up the text for that JavaScript and then interpreting it. It's actually already turned it into some internal form and executing that in memory. And I think this is correct what I'm saying. So I could be wrong. You could go look at the way Esperino is really working, but that's roughly the idea is that it's actually it's not fully like ECMAScript compliant JavaScript. It's not a full implementation because it's actually being pragmatic and cutting corners where it needs to in order to preserve RAM. And one example of that is in JavaScript, if you're dealing with a number, you might typically think of that as like a double in terms of its size. Well, on Esperino, it's like a float. It's like half the size, you know.
Oh.
So they went, you know, and just lots of things like that exist. And there's just other things that it just doesn't support. Like JavaScript has labels. You can label things and jump to those labels. Esperanto just says, it's not going to support that. It's not important enough.
Okay. So the language wise, it's a bit, it's a little bit of scaled down version to microcontroller level.
Yes. Yeah.
JavaScript. Okay.
Yep. It's like a profile of JavaScript. Yeah.
Okay. So why not write JavaScript then directly? So where did Clojurescript come into the picture here?
Have you ever written JavaScript, Vijay?
I did.
How dare you?
using jQuery a long time ago.
Yeah. Okay.
Exactly.
No, you can. Yeah. So no, you can. You could write. And Esperanto is very popular, and it's a perfectly suitable approach. Yeah.
Yeah.
Actually,
Ray and I would disagree.
Let's be honest. I mean, that was definitely the approach we were looking at as well at the beginning, because we didn't think that we would be able to get Clojurescript on these devices. We would rather write JavaScript and C, at least at the beginning, you know. So anyway, Mike, back to you. Yeah. Okay.
Yeah.
Oh, okay. Yeah, and another
how
thing
did
to mention.
Clojurescript? Yeah.
Oh, okay. So it's just because we are who we are. We wanted to like stick in the language that we were comfortable with, right? And I don't know if that's a satisfying explanation. Like I could write JavaScript,
well,
but
there's a Clojure podcast, so I think that's the reason.
Yeah. I mean, this language has value. I hope we all agree. Yeah.
Maybe it's a better question, because I think we always want Clojurescript. The better question is, why did you think it was possible, or how did you get to the point where it was possible, to execute on such a small constrained device?
Oh, okay. Yeah. So even before that, I had tried running, like for example, like the Clojurescript unit tests. I took that, like when you in Clojurescript, when you say, hey, I want to run its compiler unit tests, it spits out an advanced file that's just a chunk of JavaScript, and you could take that JavaScript and try to run it anywhere. And I had done that with like Esperanto in the past, and it never did run properly. And at one point, and this is part of what it took to get the stuff running, is just like finding out the little reasons or what it was. And at one point I ran them, and I don't recall what changed, but it worked. It worked on the Esperanto command line version of the thing. So like you can take Esperanto and put it on your Mac or your Linux box, and it's basically a shell, or it's the same C program basically. And I got it to run there. I'm like, oh wow, Clojurescript can actually run on Esperanto. And then to answer your question, Ray, like what made me think that it could fit there? I think it was just the amount of RAM that existed in that thing, and knowing that in order to actually have a REPL, the main thing you need to do to have a REPL is you need to have basically all of the Clojurescript standard library available to you. Basically, CLJS core, like map and filter and all those things, they need to be there. Or ideally they should be there. Otherwise you're dealing with a whole different problem where you're trying to say, oh, you just called filter, but it's not on the chip right now. Let me go somehow get it on there.
But isn't the toolchain then, so you write Clojurescript on your computer, you compile it to produce advanced JavaScript, and then you just copy it over onto microcontroller storage and then run it. Isn't it so you don't really need to have the whole Clojurescript on the chip, right?
Right. And that what you just described is a perfectly valid model where it's like, okay, I'm going to write my stuff in Clojurescript, compile it down to advanced, take that thing and put it on Esperanto and just let it run. Right.
Yeah. Yeah.
And that's most likely what you would do if you were like making a release build of something, and you're just gonna, but the REPL, you got to have a REPL to have the full experience. So, and if you were to do things in that mode, like where you just compile it down and put it on there, then it's almost a lot like what happens when you're just working with C, where you compile your C and you put it on the chip. Now, it's not a completely fair comparison, because typically with these microcontrollers, when you're doing C, you can establish a debugger session, and you can hit breakpoints, and But what I wanted was a REPL into the thing. I wanted to be able to, and part of the story there is things like Esperanto. What they do is they take the facilities that your chip has, like, so one thing all microcontrollers typically have is what are called GPIO pins. general purpose IO pins. So if you imagine like you want to hook up to something else, you have all, everyone, when they think of a chip, there's all these pins sticking out of it. Some of those pins are used for data to drive things, right? And when you're writing your program, you may say, hey, take this pin and raise its voltage high or raise it low so that you can light up an LED or unlock a lock or what do you want to do? Or you may want to, you're sending messages to a CAN controller and you want to like do that through GPIO pins or there's other higher level protocols above that, I2C and SPI. But essentially, Espruino takes those low-level facilities that are available, GPIO pins and whatnot, and basically turns them into kind of like first-class things that are visible in the JavaScript environment. So you can just refer to them. So if you manage to have if you have an Espruino REPL into one of these controllers, you can just sit there and you can drive your GPIO pins in real time. So
it's basically having like a file handle and then you can just write bits to it or data to it directly.
Yeah, I mean, it's so the GPIO pins, you can, they're really low level. You just say, hey, raise this thing high, raise it low. And the thing about having a REPL, and this is why Espruino itself is fundamentally a cool thing, is that you can do it in real time. You can get a terminal into it, and you can just sit there and change the world by typing things into your thing. And that's what we all think of when we think of a REPL, right? You're changing the state of your program or adding new functions to the mix. So, Clojurescript having a REPL into it is the same idea. It's just in a different language expressed one level higher. You're defining new functions, and the cool thing is that if you're trying to prototype something, it's really nice to be able to say, oh, let me try driving this line high and see what happens, rather than in the traditional C model where I guess you would change your code, compile it, and put it on it.
Copy it.
You might mess with it in the debugger to try to force things, but come on. Yeah.
So basically,
really
what's weird about it, if you look at it either way, is that embedded programming, embedded controllers or ECUs or microcontrollers, they essentially take you back to the mainframe where you're batching your programs. Sending them over there, getting them run, and then seeing what the results are. It's not usually taking all day, but
One cool example of that. There is a guy who helped a lot, or contributed a lot to Espruino. His name's Kieran Sheila. Not to confuse things by mentioning another Kieran here, but
that's not
his first name is Kieran. So he basically was working on something with Vouch, and he took one of these Espruino things out and basically with Clojurescript and was basically doing an experiment effectively with a fob to his car, and actually at the REPL messed around and managed to unlock his car that way by finding the right sequence of things, and you could figure that out the old fashioned way, but it was, he's basically, because he was in the mode where he was learning and experimenting and seeing what the fob does and how it actually works. So he basically said, I need to set this line so that it drives at low and open rate. So he could quickly iterate and just, and prototype and say here's how you do it. And then capture that knowledge, and carry it forward. But that's the kind of stuff that you can do if you have a REPL into something, is you can be in that experimental, playful mode where you're just I'm typing and seeing what happens, right?
But is there a chance that I can burn the microcontroller?
Ooh.
Or
I remember that was the old thing, right? With basic computers.
Yes.
Yeah.
You could always potentially.
You could go into Sears and type in a command and burn it out.
Well, I guess what you're saying, Mike, is that Espruino gives you kind of safe access to the hardware. So it's kind of got these high-low things that are probably pretty
the boundary.
What VJ was saying was you could actually hook up your microcontroller to something that's affecting the real world. And because you have so much freedom, you may actually make the robot break the hole in the wall or something.
It's almost like, okay, let me raise it to 1, and then I type 100, and then
And I guess that could happen if you're writing stuff in C anyway, but but it's even, you could do it much more quickly at a REPL.
Right? Yes, exactly.
Yeah, you could accidentally
Real
launch
time.
the nukes. Yeah, basically.
Yes, I think that's the experience you want to have, right? Like immediate feedback. So if you have like
Yeah.
a increase the RPM to whatever, and then I forgot to make it 20, and then I just like 2000, and then it just blows up.
The other thing though, Mike, I mean, coming back to
Yeah.
Clojurescript, is that, do you think like the fact that you had a good experience with like self-hosted Clojurescript, helped you with these embedded controllers? Because, like you say, you kind of know what's needed to bootstrap the whole thing.
Yeah. So for me, it was fair to say that I knew what it meant to make a REPL. And I mean, I think everyone's familiar with what a REPL is, but if you actually had to sit down and make one and know all the pieces, and it's not that complicated, but it gave me the confidence at least to say like, yeah, I've made REPLs before. I think I know the pieces that would be needed to make a REPL into this chip. One thing that, for example, that you don't get with the Esprit REPL into the chip is you don't get the ability to load files. So like you can't require files, and that's just a limitation that exists in the implementation right now, because in order to load so to back up a second, I'd have to explain how does that even work with Clojurescript. Like if you say, I'm going to require some namespace, right, that you have on your disk on your computer. And the way that typically works is locally, the Clojurescript compiler will compile that namespace down to JavaScript. And then the trick is somehow getting that JavaScript into the execution environment. So if you are, let's see, if you're coding in a browser with Clojurescript, typically that involves, I guess, how does that work? Since I don't deal with browsers, I don't even. Maybe Ray, how does the browser get the resulting JavaScript into it? Does it just pull it across a WebSocket or something like that?
Yeah, for Figwheel, it's automatically pulling it from the WebSocket, right?
Yeah.
But otherwise, you can just refresh it, and then it's attached to the HTML already. So one JavaScript thing is loading the other files. There is a loader, app.js or whatever.
Yeah. So you can do it like that. But obviously, you can just load it from the browser's local storage as well if you really want to go crazy.
Okay.
But so you have to get it in there first of all.
So for my experience has been like doing there's the ambly REPL, which is a Clojurescript REPL into iOS, right? And the way that works is it sets up a WebDAB, and the WebDAB is on the phone, so it becomes like a thing that you could mount from your computer, and then you have a file system, and you just make the Clojurescript compiler right there. For self-hosted, if it's Plonk, the files are just there on your. You can read them directly, right? For things like replete, you can't do that. Replete on iPhone, you can't require a file. It's just not set up for that. So for this Esprit REPL that's into an ESP32 chip, if you were to try to require a file, it just wouldn't. It doesn't have the facilities to kind of get that JavaScript over the quote wire and into the REPL. But other things do work. Like you can have your own namespaces if you'd like, and part of the way that works is when you're compiling the REPL itself to get it onto the chip, you can have it also at the same time compile your own custom namespaces that you may have that you'd like to have pulled over as well, and they would just kind of get bundled into the same thing that's put onto the chip.
So what is the? I'm trying to understand how the setup works. So I have this microcontroller, and then it has somehow Esprit installed on it. So it's working, and then the Clojurescript stuff that you said, it's also installed there. Now, how do I write shit in Emacs now and then compile it? And then connect to the REPL from Emacs.
So the way I chose to do it is I made it so that the ESP32 actually supports Wi-Fi. It actually and also supports Bluetooth. But so I basically I arranged things, and there's multiple ways you could do this, but I just arranged it so that the ESP32 will join your local Wi-Fi. So you give it the password to your Wi-Fi, and you give it and this was not something I created. The ESP32 or Esprit already had this capability built into it. And so then I just establish a TCP connection into it.
Okay.
Given
so you
that
know the
it's
IP address, and then you know which
yeah,
port it is
basically I
running.
have it exactly. I make it run a little server and listen.
Yeah.
And then from that's basically the REPL connection. And that's so like when you say, hey, evaluate some form, the JavaScript for that form is sent directly across that TCP connection.
So what does that look like in terms of like, because VJ probably wants to use nREPL or something like that to get to it. Does it support like nREPL and Bencode and all these things?
Okay, yeah. So the cool thing is Clojurescript has an ability for you to define your own custom REPLs, your own custom REPL implementation. And so it's got this base functionality in the Clojurescript shipping code base. And you can make your own REPL by basically following a few patterns, implementing a protocol. And that's all this particular Esprit REPL is one of those. And because of that, it plays in the normal ecosystem like any other REPL. And you can use Emacs. There's actually Kieran Sheila wrote instructions for how to set up Emacs to work with it. And I imagine that those instructions, I don't use Emacs, but sorry. But
okay. That's it for episode number 69. I think. Thank you, Mike. And
but I'm assuming the instructions are just like any other.
So how do you use it with a proper editor?
Like Emacs.
Cursive. I use So let's see. With Cursive, I would use this thing that I created called Tubular that basically makes it easy to hook in.
Okay.
I never did figure out the prepl thing. Sorry, Ray.
We'll have to do a PR for that one.
But to answer this, it's just a REPL like almost any other, and it really is a standard Clojurescript REPL. And apart from that deficiency where it can't load files, it looks like any other REPL.
So if you've got like a requirement where you want to do like map, filter, reduce, and it's all good. But if you want to do some sort of like closure set operation or something like that, do you have to arrange that beforehand, or can you what comes with it? What's built into the REPL? Because I know that some REPLs come with those kind of like, and I think some of the REPLs you ship come with some of these like common libraries, closure string, that kind of thing.
Okay, yeah. So the best way to explain it is the Esprit REPL is partially a tiny little Clojurescript program that implements that server that I was talking about. So it actually like does all the REPLisms, all the things that it needs to do to be a REPL. And in that Clojurescript namespace that implements that REPL, whatever it requires ends up being in your target environment. So like Ray, you mentioned, what if you want to do something with closure set? If that thing is not already including or requiring closure set, then it just wouldn't be there. You'd have to like either add it to that REPL or add it to another side file that you're going to have compiled with the mix and have it over there. And then it would just be there. It would end up getting put together. And what happens is the way this works is when you compile this thing, when you compile the little Clojurescript program that represents the REPL, it gets compiled down, and we use so in the Clojurescript compiler, you can choose like advanced, or typically when you're dealing with a REPL, you do none, or you could do white space and simple. Those are different like closure modes. So what we do specifically for this Esprit REPL is we do simple, and simple is basically a fairly compact representation of things, but it has this characteristic where it preserves all the top level functions. So map and filter and all those things are in CLJS core are still actually there.
So they're not minified, or they're not having this weird naming like in advanced compilation.
Or mangled. Like the insides of the functions might get mangled and minified, but the top level,
So you can actually see all the symbols pretty easily and then use them.
And so the part of like, I guess me delving back into the how is what happens is it produces a simple output, which is one big concatenated JavaScript of everything needed to run everything. And that's typically, if you go back to Clojurescript and the way it works, when you apply Google Closure to it, it's doing whole program optimization across that big file. Well, that's the actual file that we take and we put onto the microcontroller. And we put it into a special, to make this work, we actually had to take Espruino and kind of modify it a little bit. And one of the modifications we had to make was to repartition. There actually is, like, on the flash, there's partitions for different places of things. Yeah. And they had one partition which is called JS code. And if you put anything in that, any text into that partition, when the Espruino engine starts up, it will, like, execute whatever JavaScript happens to be in that particular partition. So we basically just put our
everything
simple into there, and it wouldn't fit normally. That was one of the things that had to be solved. And the solution to that is to figure out how its partitioning scheme works and just make a gigantic partition, that can hold. And it has to be about 1 megabyte in size, because simple, when you use simple to make, CLJS core, it's about 900 kilobytes of text,
I think this is like the other end of the spectrum, right? Because people who are writing the web programs these days, I mean, nobody cares about space or memory or anything. So, and we just add like 1 million node modules and then see what is going to happen.
And you have to be really
the browsers
careful.
became But here you have to be very careful in what you're adding and then how much you have.
Yeah, but I think that's a bit unfair though, VJ. Things like Yarn and stuff like this, they strip out, or they do all the tree shaking before you ship it out. So
that's true. But it's not, I mean, I'm talking about normal websites these days, which have like 1 million trackers and all the crap and everything.
All the cookies and the trackers.
Yeah, exactly. Yeah.
Well, I think IoT will eventually get to the point of, I think the idea that the browsers are the only place where the surveillance state will exist is, probably optimistic.
So people will be installing a Google ad blockers onto microcontrollers.
Yeah. Well, Mike's already kind of like bit mining on the ESP32, I'm pretty sure.
Oh man.
So you're mining cryptocurrency on that one.
Good, yeah. I have quite a few of these things lying around. I might as well put them to good use.
So what is the memory efficiency of these things? Sorry, not memory. Power efficiency. So how much do they need?
So the coolest tweet I have on that subject is I had one of these REPLs running, and it was using less than half a watt, I think, of power to run. Yeah.
Yeah.
So it's like, these things, and that's, you could actually, like, the way these things are designed is you could put them to sleep, and kind of have them wake back up again. So you could even amortize and get like almost no consumption.
Yeah.
Well, but one of the other things though, Mike, if I remember rightly, coming back to the beginning of the discussion, was that you wanted to talk about like the startup time. Because Raspberry Pi was like taking a while to start up, and all the booting and all these things.
Yeah, that was one thing that caught me off guard, was how microcontrollers are like instantly on. Like, you turn the thing on and it's running, like, and that's just weird to me. Like, I think it's weird to a lot of us who are used to things having to quote boot, right? There
is no startup ding, like ding.
Yeah. So like,
starting.
Well, there isn't like 1980s BIOS running on there.
Right. Yeah. So it like runs your C program immediately. And if you get Espruino and you put it on one of these things, you boot the thing, and it like, maybe it takes like a second. It's not instant, but and then your JavaScript REPL is available. You can start typing commands like that within a second. And the thing about Clojurescript though, is there's that megabyte of code that it has to like run upon starting. So Espruino fires up and it's like, let me go see if there's anything in this JS code partition. And it runs that. And that code takes about 15 seconds to run.
Wow.
So when you start the thing up, it just, it takes about 15 seconds to load up basically CLJS core. You could look at it that way.
Yeah.
Now there's things you could probably do to make it faster. Yeah.
But you don't have this. I mean, this is only for the development mode, right? When you want to actually have a REPL into it, because on production you have the instant loading stuff anyway.
Yeah. So you can do advanced, and I think my memory is fading now. I think I got it. I think the numbers are around 4 seconds if you do advanced. Okay. So it's not instant. And I even went down. This is one thing I kind of like went down this rabbit hole of trying to see like how fast you could make that work. And it turns out like if let's say you make a simple program that does some stuff. Like it does a reduce and calls a few map calls, like maybe like a program that's not trivial, just does a few things. But it's not like a a gigantic program. It's just like, imagine like a 15-line program that you want to like start up and do something. Yeah. And I went through that exercise and I made it be advanced. And then I found, interestingly, that Google Clojure compiler, which does dead code elimination, it actually leaves a lot of code behind that it doesn't know is actually dynamically dead. It does static analysis to see like things that it knows cannot be called. But in fact, there was like, I want to say, if I remember correctly, like 2/3 of the code that was in there was like truly never going to be called. It was, and so I went through and I spent like an hour and I would like remove a function and see if it still worked, and just like went through. Yeah, I know. I was like, I was a man on a mission. I wanted to see like how small I could make it, and I went through, and that's where I think I got like 2/3 of the code gone, and the remaining bit was the stuff that actually was needed to execute this little non-trivial program. Yeah. So that's kind of an interesting point, is that Google Clojure compiler, when it's doing advanced, is only getting rid of stuff that it statically can see is never called. There's still a lot of stuff that dynamically is never called, but yet it just can't tell.
So we have Clojurescript REPL now, but that is not, I'm assuming, obviously it's not going to be in production, because otherwise, people will be just connecting to my car chips and, REPLing into
So,
into my
so
cars.
To be honest, like a lot of the stuff at Vouch of what we've done is we've actually stuck to like more pragmatic, traditional ways of doing things with C. To make solutions that will, like, if you think about cars have ECUs in them and you're going to like perhaps make some code that's going to run on an ECU. I don't think we're there yet in terms of like these higher level languages running on ECUs. Maybe another half a decade to a decade, it'll be like, this stuff is fine, and those ECUs will be much more powerful. But for now, I kind of think of this whole thing as like a foray in that direction, where you can like experiment and see how things work. But And it also is like a little slow, right? It still is like, if you say, I want to unlock my car, and it has to turn around and like maybe process a CBOR message that you send across the wire to it, you're starting to run up against performance problems where you're like, maybe I should do this in a native language still. But those things change, right? Given the few years going by. Yeah.
Exactly. Yeah.
Well, especially with your comment about JavaScript running very fast,
Eventually we'll get there. Cars running on Clojure.
Well, another thing is like, for example, Scala has an equivalent Scala.js, like a JavaScript analog. I think it was like maybe 2 years ago now, somewhere in there, they came out with a native thing that compiles Scala down to native. And Clojure is starting to have the same thing with Graal, right? You can basically make native things. And I think that's ultimately an interesting thing for cramming stuff down on these microcontrollers. This is, you can somehow take these high level languages that we're writing code in and compile those down to machine code. And just, that's the thing you put on the chip in the end for your production delivery.
But don't you think not don't you think, but what's your opinion on cutting the middleman, then completely remove the Espruino and then make Clojure compile to C then?
That's exactly what I was trying to say. Yeah. Thank you. You said it better than me. Basically, no, that's exactly it. Clojure compile to C. Or either C or even if it knows the machine language of the particular chip you're targeting.
Exactly.
But C might be a good intermediary. Yeah, exactly.
Because then you cut the middleman completely, and then you have much more, I don't know, there is no reason to have another.
Well, I think the other way is looking at WebAssembly, isn't it?
WebAssembly is another path to get there. Because what you also kind of need is like garbage collection to make this language work. And I think WebAssembly might have an answer to that now.
It does.
Originally it didn't, but
on
I
the
think
browser it does anyway.
Okay. Or maybe you could even do like reference counting, kind of like they do
probably,
with Objective-C and Arc.
Because I understand you're working in the cars domain. If you move that to a general purpose thing, what you're saying is that I can get these ESP chip, put your program there with CLJS REPL, and potentially I can connect to, I don't know, some other Bluetooth devices like my lights or whatever, and then use Clojurescript to drive them. Is that a possible scenario?
Yeah. So in theory, like, so Vouch for a while, for some of the prototypes, we were using ESP32 boards or ESP32 chips on our boards, and we would program them in C. But in theory, everything could have been done in Clojurescript. It would just be slower. But there's conceptually, it's Turing complete, right? Anything could have been done that way.
So we can connect to some other Bluetooth or whatever or Wi-Fi thing, and then send signals to other connected home devices by writing Clojurescript program.
Yes, essentially that's the dream.
Yeah. Because the closest I got to this level was I had this NXT thing on Lego. Well, I still have it, NXT3.
Yeah, I know what that
small
is.
thing. Yeah.
My son has one of those. Yeah, like a Mindstorm.
Yeah, exactly. Okay. Mindstorm NXT3. And then it came with the Lego's operating system, some shitty thing with the blocks and nonsense and other stuff. So I had to flash it with something called Legos, Legos. So that actually brings JVM onto that thing. Okay. I remember experimenting with that one with Clojurescript back then, Node Clojurescript on this one. It was incredibly slow to do anything on that one. I mean, you can imagine there's already Java, and and then rest of the shit, and then on top of it, this Clojure plus Node Clojurescript.
If you hook up to an ESP32 with Clojurescript and you do say map inc over the vector 1, 2, 3 and hit return, it will do that in a matter of like 2 seconds. Say it's not blazingly fast, but as a human you can deal with that. But if you say like do that over like reduce plus over range 1000, that actually takes like 20 seconds or so, somewhere around there. You have to be careful. So it's like at this current point, you can only really use this to kind of like be a high level coordination of actions that may be themselves implemented in native things.
I think what you're trying to say as well, Mike, is that like based on the previous examples, is you want to try and do interactions with the hardware facilities interactively. That's really the benefit that we're getting out of it, not necessarily the the kind of
general purpose,
usage across in sort of like setting up your smart home using Clojurescript is still a bit distant, in production, but it's definitely super useful for experimenting with these kind of things and driving these different parts of the embedded devices capabilities that you wouldn't easily get with other languages.
And like what's happening big time in that whole space is Circuit Python. I mean, people are starting to see that you can just use that as a high level language to interact and drive these chips, and as opposed to like, I mean, I wonder how many people even know C these days, to be honest. Like if you like, it's just so much more accessible to everyone. If you say, hey, you like, for example, a lot of the people who are into hardware are not also programmers, right? And vice versa. Programmers are not into hardware. So like for hardware folk, if they say, I just want to, I know the hardware stuff. I know how to do voltages and resistors and LEDs, but yet they want to program their thing that they just made. Then they're faced with this another whole problem. And for them, the answer is probably not Clojurescript, right? That's but Python, it runs on the shift. So that's becoming popular. It's like, you can program stuff in a higher level language. And even for people like us who are programmers, it's easier to do something in Clojurescript than it is in C, right? C doesn't have a map, right? If you want to build a map, like, you know what I mean? That pain, it's like, you're like, how do I do this? Oh, I'm going to make a fixed size buffer and put pointers in the thing and walk that buffer. I'm going to try to, you know where you've been there.
Yes.
It's like, even if you are an experienced programmer, C is really
still
painful. It's just,
I think once you get used to like Clojure level, exactly. I mean, it's just, exactly. It's nicer looking assembly pretty much, C at this point. So I think once you get used to these higher level, I mean, C is supposedly higher level, but even one more level, highest level programming, like Clojure and everything, it's pretty difficult to drop into that level and then lose all the idioms that we use. So how do I get this thing then? So I just go and then buy ESP chip?
Yes. So if you want to mess around with this, the main thing is there are different ESP32 variants, and you got to make sure you get the one that has the RAM, all the RAM. And there's this version called the W Room, which is the smaller one. You want the W Rover, the bigger one. And maybe we could put show notes in. because it'll be hard to remember. But there's like a 16 megabyte version, or really, you only need like the 8 megabyte version because Espressive, the folk who make the stuff that you use, the tooling that you use to code to the ESP32, even though some of these bigger chips have that much RAM, they don't make it's not possible to access all of it yet. So you only need like 8 meg. So you can buy, assuming you can convince yourself that you're buying the right one, you can buy one of these things off. And it really is. Like Philip Meyer helped me with this when he's also in the Clojure community. He helped me like pick the right one. Like, it's like, because, you go on Amazon and there's so many of these variants and you want to like get the one that has the right amount of RAM. And then as long as you have one of those, you can get the Esprit REPL and hook it up to it. It's all you need. No, they all come with Wi-Fi. You're all good to go with any of that. You can then any of these off the shelf ones can pretty much work. I also made one for myself because I was interested in that, but you don't need that. That's just it's basically the way you could look at it is these ESP32s. If you back up a little bit, they are basically a chip that's inside of a thing that you typically would call a module. And it's a larger thing that has like a big silver RF can on it. And so it's the low level chip with enough stuff supporting circuitry on it to make it work easily. And then typically those things are sold on a board, a development board that has like all those pins broken out into GPIOs and additional circuitry for USB. So you can plug in your USB into it. And those are the things you can find on Amazon or wherever you want to buy them from.
So you just buy the board instead of just the chip, just the microcontroller.
Yeah, because if you buy the microcontroller, then you're going to have to solder it onto something or
But you have this CLJS board thingy, right? That you
I just kind of did it I was giving a talk on this stuff at Clojure North, and I wanted to make something for the talk basically to kind of show it all working. So I made a board that has this chip on it. And it has like, for me, it was also just kind of fun to learn how to make all that kind of stuff. So I put like, a lot of these boards will have the ability where you could plug a battery into it, a lithium ion polymer battery into it. Well, I wanted to make one that, and I don't know if these other boards do this, but I wanted to make it so that it could recharge that battery. So I wanted to make it act much like a cell phone, where if you plug it into USB, it's charging it, and then you could disconnect it. And for me, it was almost like a gimmick, but I wanted to make it so that the REPL could work just on Wi-Fi, right? So you can hook it up and get all the stuff flashed to it, and then you establish your REPL into it, and then you can disconnect it, and it's sitting there running, right? And you're actually still controlling it through your REPL over, a Wi-Fi TSP connection. So that was part of my motivation, was just kind of like to learn how to put all these things together. So if you want, you can buy those on Tendy. My daughter actually makes them. So there's a video that I have where so essentially a big part of it is taking all the little electrical components and putting them on the board, right? So the way PCBs are typically made is there's robots that do it, right? And they're called pick and place machines, and they'll put things on there. Well, my daughter is a pick and place machine, so because we're not making enough of these things, where you're not going to have like a huge production run of like enough to justify that, firing up the robots. So my daughter is a human pick and place machine, and she makes these things, and we basically put these boards up on Tendy. So if you want to get one, you can get one there. That and the cool thing about it is it has like a little Clojurescript logo on the board, on the PCB. But it is no different than in these other things you can buy off of Amazon or wherever.
But it comes pre-built, or how do you call it? Like pre-installed, pre-flashed with Clojurescript.
So that's what I wanted to do. Actually, I wanted to do that. But the thing that prevents you from doing that is you have to like basically get your IP address, or you have to get it to join your Wi-Fi. And there's ways to kind of like make it so that it could, like, I guess I could do that and like make it do a hotspot.
You already have like a manufacturing, how do you call that? Like a flow,
an assembly line.
You need to have like a QA assembly line, exactly. And then you have like a QA controller, and then
so it is so close to that.
Build this one.
So that was my initial dream, was just say, hey, if you get one of these, it's already and you just kind of, I wanted to make it even work over Bluetooth. So you could just like power the thing up and then see it through the REPL through Bluetooth, and it would just discover it and it would just work. Right.
Yeah.
But it's not that way now. You basically get the REPL and you compile it and you flash it onto it and you follow some instructions. And this is the stuff that Kieran Sheila, kudos to him. I made the stuff fundamentally work, but it was like messy. He came along and like made it nice and polished and like added like a lot of the depth seed and aliases and scripts around it to make it like all automated so that you could do it without going crazy, you know?
Nice.
So it's not prepackaged, but it's thanks to the stuff that Kieran did. It's pretty turnkey. Yeah.
Well, I mean, it has the CLJS logo on it, so that's the most important thing.
That was one of my motivations. I wanted that logo on the board. Yeah. And I also on that board I put as another little gimmick as I put little read eval print LEDs on it. Because I'm like, oh, you know, as you are using it, because like I said, like if you evaluate a form that takes a long time, it basically the eval light will sit there and flash while it's doing it.
Wait,
you know?
is it really read eval? Like it's gonna turn on at that time, or is it like one of those turbo LEDs that we had on the computers back then? Like they don't do much.
So there is a little bit of faking involved where like the read is actually done on your computer, right? When you're typing in a form, right? Yeah. It's done there, but it will like light up that light before, you know, right around that same time. And then once the JavaScript is sent over there, right? And then it's like evaluating that JavaScript. Maybe it's like reduce plus range 1000, right?
Yeah.
And that's like blocking the main thread inside there, right? When it's doing that, but it flashes the LED by telling it to do what's called pulse width modulation, PWM. And it basically uses a low-level facility of the hardware to say, flash this LED at this certain rate. So it starts it flashing and then stops it when it's done. Yeah. But it's a gimmick. It's just kind of cool. You know, if you're going to have a board that's got a REPL, you need those LEDs on it, right?
That's totally cool.
Yeah, certainly. So it's read eval print and then light up, and then there is all four of them lighting up like a firework.
It's also got another LED that will tell you like if you're connected to it or not. You know, little things. And there's also 3 other LEDs that you can use that are RGB LEDs that you can light them up. You know, if you just like if you hook into the REPL, you can evaluate forms, but then you're like, well, I want to actually do something. So there's some LEDs on there that you can light, and there's GPOs. You can hook it to other stuff. Nice. If you're interested in it, there's a part near the end of the Clojure North talk where I give some demos of doing stuff with the board that it actually interacts with the real world.
Nice.
But
it's a fascinating journey, right? Taking Clojurescript closer to the hardware, almost like near native.
So Mike, what about like getting Clojurescript on even smaller devices? Because I think you did try that. You tried to put it on some smaller devices at one point, didn't you? And partially loaded the REPL and then sort of brought in other functions on demand.
So that's like if you think about it, like Esperino works on even lower end hardware that does not have like enough RAM to hold off all of CLJS core. So you could imagine arranging things so that you could at least establish your TCP connection into it. And then if you typed in something that said map, filter, whatever, and it hit those functions, it could perhaps fault them in. But I haven't gone that far. I've never built that facility in. But that might work where you're like, because then it would fault in what it needs as it needs it. And then perhaps that fits in the RAM that you have available. But it's an interesting journey. And,
But you said that maybe probably last question, because you said that Esperino is a kind of a smaller set of JavaScript, right?
It's a subset, yeah.
So that didn't pose any problems for any of the Clojurescript compilation modes then, so far?
So the main thing that I ran into is the lack of support for labels. And for some odd reason, Google Clojure compiler emits labels in the code. And what's the reason I say it's odd is because when I look at them, you say, here's a label. And you go look at it, and the label seems to be unnecessary. Like it's just sitting there on a code block, so you can remove it, right? And it's like really weird because that's the whole point of Clojure compilers, to make the code be as small as it can. So that was, to answer your question, that was one small problem. There's some other things surrounding, like, I can't remember, like little things here and there. And what we do is, this is kind of painful. When you basically use the Esprit tooling to say, hey, make a ROM that I'm going to put on there, it basically does a pass over the code, and it modifies the code to remove labels and stuff like that.
Okay.
And that's the painful part, is that it's not using anything to parse the JavaScript. It's just kind of like regular expressions, or basically. And this is actually kind of a thing that David Nolan, one time I was talking to him about new things to add to the Clojurescript compiler. One of the things he has in mind is at the I don't know if it's the back end of the compiler, the part where the code comes out. That part that emits the code. That part is kind of vulgar in the sense that it just spits out strings. It spits out JavaScript. And you could say, well, we could probably be a little bit more sophisticated and spit out like an AST or something like that, some sort of representation that could then further be manipulated by tools. And if it did that, then this Esprit tool could say, oh, I'm going to go through and basically get rid of the labels programmatically more easily, things like that. So there are a few things, and I was surprised though. Like, it actually, like, as far as there could be things lurking in there that haven't been discovered yet, but when I set up a REPL and interact with it, everything works. I haven't been able to find some code that breaks it. Having said that, I just tried the latest version of the Clojurescript compiler that's not been released yet, just to see if it would work, and it broke. There's something that gets emitted with like arrays in a weird way that's like, basically like you're talking about some feature of JavaScript that it doesn't understand.
I think that's a fair point, right? Given all the constraints and the amount of stuff that you're getting, and you can have the complete Clojure core then, right? When it's not just the first level functions, but also Jext and whatever the things that are implemented using MapReduce, and then higher level ones as well.
Basically all of Clojure core. And there's space to have even more like Clojure set and whatnot. So it's not like it's completely full. Like if you have, I don't know if I've even tried this. Like, if say you wanted to use like core async or something, some library that's, another library, you could bring those in as well. And they theoretically would work, it's all, there's nothing, this is not like self-hosted where it's like, maybe it'll work, maybe it won't. This is normal Clojurescript. And the only real constraint is whether or not you have enough RAM to hold all of it, and whether or not Esperino's implementation of JavaScript can cope with whatever you throw to it.
Nice. Super awesome. I think it's a completely different topic so far. I think in the past 4 years, I think we never went into this direction with Clojure, the lower direction towards the hardware and microcontroller levels so far.
It is novel. Even to me, still, it's very novel.
It's super exciting because we always talk about like the web, frameworks or whatever, Clojure in the front end or JVM, and pretty much all we are kind of stuck in the we don't care about memory. We are already running Slack that is eating 20 gigabytes RAM. So who cares?
This is a new like engineering challenge. How would you get this stuff to run on there? And even if, like, let's say it's solved, let's say someday we come up with like a native version of a Clojure compiler, like that would be just beneficial for like command line tools and whatnot. And anything we might want to write, like even a server side program that's native could be. I don't know if that's a good thing or not, but it would start up quickly, right? Like maybe like if you're trying to do like what are they called? AWS Lambdas that where they need
start super instant. Nice. This is super exciting. I think so people can order it from, what is it again? I'm not familiar with all this hardware.
It's called Tindy. Tindy. So Tindy is a place where like if you make your own little project board or whatever, and you're like, I just want to put it up there for people to buy. It's a marketplace for those kind of things.
It's like Etsy for
Etsy for electronics.
Yeah, basically. Okay. It was kind of cool. Like because the Clojure and Clojurescript community took some interest in it at the time, this board went up near the top of that list on that marketplace. It's like, cool. It's like we're representing. We're like we're like basically introducing other people and other this is actually truthful. There were other people in the hardware community. There was a bit of crossover where like people in the hardware community are like, what? There's this language that runs another language that runs on MCUs, and they take an interest in that kind of stuff. And they're like, well, it's Clojure and Clojurescript. So it's good for us, right? It gets the whole Clojure and Clojurescript name out there, to a new crowd of people.
Yeah. So it opens up new audience.
Yeah.
New people.
Yeah, you've been on these embedded podcasts, haven't you, Mike? They only run on ESP32s now.
So I was.
You have to buy them an ESP32 to listen to the podcast. That's what Mike is doing now.
Yeah, I've got the secret handshake now to get into those places. Yeah.
So you can buy the Clojurescript podcast version of ESP thing.
Yeah,
I think.
Yeah.
No, but you have been. I mean, in all seriousness, you have been like spreading the word to these YouTube channels and other places, haven't you, about like how it runs on these smaller CPUs, smaller controllers.
Yeah. It's kind of like there's the Clojure community, there's also the hardware community, and there's a small intersection between the two.
Yeah,
where they meet.
Nice.
So yeah,
but it is super exciting, and I think we are almost a pretty much reasonable size of the podcast already episode.
Cool, yeah.
But this is super exciting stuff, Mike. I think we'll put a link to Tendy.
Yeah, and you could go check that out. Go on Tendy and search for Clojurescript, and you don't even have to buy one of those. Just go get one off of Amazon. And just get one and mess with it just for the wow factor, just to, like,
exactly.
It's novel. You're like, oh man, I have like this little tiny thing running Clojurescript.
Yeah. I think
it's just cool.
Enough of free framework now. Just go and run this on a small microcontroller and then get excited. Yeah. I think that there is some sort of a visceral thing, right? I mean, when you write these, okay, this is the same feeling that you get first time when you write JavaScript to run in a browser to do something. That's so exciting. And then now everything is layers and layers and layers, and then we get used to it. But I think every time I do anything with the small Arduino board I have, and also on NXT thing, it's kind of magic to see, like, I can control the RPM of that small Lego motor with some C code somewhere, which is super exciting to see the real world movement stuff.
The feedback
thing that this is,
yes, yeah,
and this thing's it's just all about like empowerment now. Like if you know that this thing exists, if you say, I want to do my Lego Next thingy with Clojurescript, you now know that you can.
Yes.
It's pretty much all packaged up for you, and you can just go get it and get one of these little boards and hook it up to your system, and just knowing that you can do that is good to know, right? Because who knows what kind of project you might be on next, or some hobby thing you might try to do. You might want to build a cat feeder or something. Who knows?
Exactly.
Important things in life.
Yes. I think solving day-to-day problems properly with Clojure.
Yeah.
Instead of building yet another web application. But super nice.
Cool. Yeah.
It's super exciting, Mike. I think thanks a lot for explaining all the stuff. I know, and it's still
I feel
it's still pretty hardware. How do you call that? Like level stuff that I don't understand that much. But I'm pretty sure bringing Clojurescript there is like an awesome stuff. So you can actually REPL into something and into the microcontroller, which is amazing. But I'm pretty sure I think this is supported by your company as well. So much.
Vouch has supported me in making all this. Yeah, it's very much the case.
So they're vouching for your CLJS boards.
Oh
yeah.
But I think it's interesting with these boards. To some extent, in the whole IoT world, is just the cost of the boards is so low. That you can afford to buy them just for fun. You don't have to spend €1,000 on these things.
Yeah, the main chip, if you were to buy. So I think the Amazon boards that you can get are like on the round of US dollars, $15 US dollars, somewhere around there. If you get the actual ESP32 chip, and you like design, if you're into making your own boards and you want to solder one onto something, the chip itself is like $3 or $4 US dollars for one of those. And that's, like if you were to actually just get the chip by itself, that's getting down to like $1 or less,
Yeah.
So if you ever want to make something inexpensive,
you just use one of these things, and then write Clojurescript on it.
Yep, exactly. Yeah.
Nice. So you're not gonna. I mean, I think if you go and buy Mike's chip, it's not gonna break the bank.
No.
And if
But
nothing
it's
else,
not
like
just
you
the
say,
chip.
if nothing else, it's a nice little like souvenir in your bookshelf or something for the next pandemic.
Hey, it has REPL LEDs. What else do you want? I mean,
Yeah, so for the next pandemic, you can have it in the background and impress your friends.
Yeah.
Yes, like on your Zoom call, certainly this is going to be something that you can show, and then
Exactly.
and then maybe hook it up to, I don't know, like a network REPL or something, so everybody can collaboratively turn on the lights on and share it on a Tmux thing. Nice. Okay, on that shiny REPL note, I think we reached the end of the episode number 69, and I think we're pretty much starting again with Mike. So it's super excited to have you back, Mike. And
maybe another 4 or 5 years from now, I'll be back on again.
Next time with complete Clojurescript running natively on the microcontroller. Who knows?
No, it'll be like a quantum computer at that time. Or something.
Yeah, exactly. Yeah,
5 years.
Quantum Clojure. Quantum Clojure.
Yeah.
Nice.
You heard it here first, folks.
Or maybe if it is quantum Clojure, then it won't be forward in the time. We'll go backward in the time. We can just time jump to anything.
Yeah,
that's true.
So that's going to be crazy then.
Wormhole. Yeah.
So it doesn't necessarily be in the future. So it might be in the past. Who knows? So we'll open a time warp thingy like MCU. we come back to MCU, like microcontroller units to Marvel Cinematic Universe. Back to square one. Okay, so that's it from us for this episode. And so go and check out the stuff on Tendy. Search for Clojurescript and then get your REPL on your microcontroller, the ESP. I don't know what ESP means. It sounds like extrasensory perception or something. I don't know.
Yeah, I don't know what it means either, actually.
I think it's from the company, probably. I think that's it from us, Mike. Thanks a lot. And so keep listening and then keep hacking. Now you can even hack hardware with Clojurescript. So what is stopping you? So have fun. Thank you for listening to this episode of DefN. And the awesome vegetarian music or the track is Melon Hamburger by Pizzeri. And the show's audio is mixed by Wouter Dullert. I'm pretty sure I butchered his name. Maybe you should insert your own name here, Dullert.
Wouter.
If you'd like to support us, please do check out our Patreon page, and you can show your appreciation to all the hard work or the lack of hard work that we're doing. And you can also catch up with either Ray, with me, for some unexplainable reason. You want to interact with us, then do check us out on Slack, Clojurian Slack or Clojureverse, or on Zulip, or just at us at DefN Podcast on Twitter. Enjoy your day and see you in the next episode.